All right. Well, we're past time on the talk, but we're now into the final discussion, general discussion phase. So I guess the question I have is, does anybody have any questions? I know we had some questions that might not have been fully answered for some of the earlier speakers. Any anything?
I would like to get some feedback. I didn't use my time that wisely, but I've been able to correlate marine chord cyclothems in the Kasimovian in the western part of the Dunkard Basin with what I believe to be non-marine ones in the Charleston area, in the sort of 50 to 60 kilometer to the east. And I never really published a paper in 2017 on that. I really haven't heard much one way or the other about that. And I think that that's a topic that, you know, being able to recognize and correlate the marine with the non-marine cyclothems, I think is pretty significant in these basins. And what kind of differences in response do you have? What I see in the non-marine section is the same thickness of paleosol bounded cycles and a transgressive lacustrian unit on top of the paleosol, followed by a coarsening upward sequence, which looks like a lake fill. You have lakes, coastal plain lakes that are then filling in with splays and that sort of thing. And then you have another episode of incision and coeval paleosol development during that next. So these cycles are remarkably parallel, very similar in thickness, and the only difference is that the paleosols in the non-marine, so-called non-marine intervals, are considered non-marine limestones. Now you have to bring the water table up to go from negative accommodation to positive accommodation, so you can accumulate some of these things. But these limestones, they include what used to be called Spirorbis. We now know Spirorbis is actually a microconchid, which is a lophophorate. And some of the more recent work on these indicates that you can't grow these in a purely freshwater setting. You can bring them in with intermittent connections with coastal lakes, but if it's an entirely isolated coastal plain lake, then you wouldn't be able to get any of these microconchids in it. And so what I see in the middle of the Glenshaw, which seems to be equivalent to these four or five marine units from the lower Brush Creek up into the Cambridge and so on, are 4 or 5 microconchid limestones, again, arranged on top of these paleosols in positions that are very reminiscent of transgressive limestones that we normally have brachiopods and crinoids.
So I think Jörg Schneider wants to comment on the microconchids and what they mean environmentally. Jörg, can you? Is your microphone on? You need to unmute yourself.
I don't trust this microconch story because we have microconchs very common in truly known marine limestones in Europe. We have them in mass occurrences in black shales, truly known marine black shales. Don't trust too much this microconch or spirobeads as indicator of any marine influence.
This is in the Pennsylvanian you're speaking of now? You're speaking about Pennsylvanian spirorbid, so to speak?
Yeah.
Okay.
Yeah, I'll add to that too. I mean, we're talking, remember there was a paper by Beth Kordesch and others about microconchs, and then there was some rebuttal by Zayton and others. And this is Triassic, but I have a phytosaur skull, a reptile skull from the late Triassic of eastern New Mexico. It's totally encrusted in microconchs. And if you draw the river system, it was at least 1,000 kilometers from the Pangaean shoreline.
Wow.
So I think you have to be, I mean, and Zayton et al. Rebutted Kordesch. I'm not sure they're as ironclad of salinity indicators as some people think.
Okay, thanks.
Let's see, John Knight has a comment or question. John, can you unmute yourself and turn on your video, please?
Yeah. Hi, everybody. There've been some tremendous talks today, and I must say that there are a couple of them that really sort of touched on the whole Earth system approach to understanding that Kasimovian period. Particularly, I'd like to congratulate Sophia, and I think Lynn also, from giving that Earth perspective. But one of the issues that I fear that we're focusing very much from our sedimentological and paleontological view, and perhaps not taking on board, is the extent of orogenic activity during this Kasimovian period. As I understand it, I could be corrected, it's not my area of speciality, apart from in the northern Spain, but it is the Kasimovian falls over a period where some of the most active orogenic episodes were coinciding. I believe I'm correct to say there was this would include the Urals, the Appalachians, certainly the Veriskides, and undoubtedly we were talking about a degree of activity which was throwing up really significant orographic barriers to systems, whether it happened to be sort of wind, marine circulation, migration of any of the terrestrial life forms. These were significant events, and I think we're perhaps, I would have liked to have heard anybody who today could have given us a synthesis of the implications of this. And just to sort of not go on too much on this, but related to this, there were clearly a number of convergent boundaries, plate boundaries. We know in Europe there were certainly significant volcanic episodes of a sort of in the acid intermediate range, very indicative of explosive Plinian volcanism, almost certainly related to convergent boundaries. Within the Massif Central, for example, in a period of probably no more than 2 million years, there are at least 20, if not 30, individual Tonstein horizons. Certainly in some of the Spanish basins, we have a similar number. We see big volcanic episodes in southern Spain, in basins now preserved in the Pyrenees, in the Massif Central. I'm sure Jorg and Stan will be able to tell us more about volcanism in Central Europe. So I just feel that in our discussions on dust, on climate modeling, on potential migration, we perhaps are overlooking something that at this particular period in the Pennsylvanian was actually hitting a real high spot of effect on a global basis. So, you know, I hope it's a useful comment, and I'd be interested in anybody who can put me right on it. Thank you.
Maybe Jorg could comment on that. You need to unmute yourself, Jorg.
Concerning the Western orogeny in the Central Europe, the peak was over already in the Visean, in the early, so-called early molasses of East Germany and Poland. We made dating of granite cobbets in this cross-clastic fan deposits, and we made argon dating of mica. It comes out This mica comes from the metamorphic core complexes of the Variscan origin and the granites as well. Means granite induced in a depth of minimally 7 kilometers. And if we have granites and high metamorphic rocks, pebbles of high metamorphic rocks, already at the end of the Visée, means at those time the metamorphic core complex and about 7 kilometers of rocks has been already eroded. That says there was no furthermore a high mountain range. So, and this orogeny, as we know, moves through time. Hercynides, Mauritanides, or Chita, and the mountain ranges move to the west and get eroded in the east. When we have the highest mountain ranges in North America, in Europe, hills only. And the same comes through for the peak of folding of orogeny in the Cantabrian Mountains. This was later than the Central Europe. Possibly Westphalian time also. And yeah, this and forget this Central Pangaean mountain range. This never exists. This was a moving range from east to west. And concerning the volcanism, the largest volcanic complexes we have in the what is in North Germany. There we have thicknesses of they have not been penetrated by wells. One of the wells, well Miro, drilled in the 17th, stopped after 2,000 meters of vulcanites, has not penetrated the vulcanites, and this vulcanites, this huge vulcanite complex, is of late Carboniferous 300, around 300 millions to early Permian age. So, of course, we have had a very intense volcanism during late Pennsylvanian and early Permian, but I don't see really an influence on climate development. Thanks.
I wonder, though, I think John brings up a good subject. I mean, let's face it, nobody really talked about tectonics and volcanism. We focused on climate and cyclicity in fairly tectonically passive areas. And one has to wonder, you know, even if everybody I think knows this, that the Hercynian megasuture, as Ziegler called it, all that would have migrated from east to west. So there must have been a lot of micro environments that were intermontane basins, at least, or, you know, and so you have to wonder about those effects. And of course, if you have this enormous pile of volcanic rocks in Germany, that implies some substantial volcanism, which might have affected climate. And, you know, so I guess, you know, I'm just, you know, I'm going to be simplistic about it. In a simplistic view, and I want to ask this question. This is the bad question. I would love somebody to give me a 5-minute summary of Kasimovian climate, in a sense. And of course, I know the factors we've talked about are glaciation is going to be a factor, certainly circulation and all that, and the you know, assembly or post-assembly of Pangaea. But you know, again, it's hard for me to believe. I'm kind of where John is, that you would smash all this stuff together. Maybe the mountains weren't high. I don't believe they were either. I don't think the ancestral Rockies were high. I don't know. I'm not sure. I don't agree with Lynn Soreghan about how high they might have been. But I just have to wonder, the effects on the biota must have been substantial, at least in local, and you know, particularly on the terrestrial biota. Yeah.
Yeah.
I mean,
So Spencer, I actually don't know how high they were either. I don't necessarily think they were very high. I think I think some of them may have had ice, but the crux of that argument is that that they wouldn't have been as high as places that have ice at the equator today. So do you understand that? So what I'm trying to say is that I'm not saying that they were 4,000 meters or 5,000 meters. What I'm saying is that we see evidence, we're hypothesizing that at times, and not necessarily the Kasimovian, because this is not well dated, but at times during the late Paleozoic, that some of those uplifts may have been glaciated. And it's important to understand that because we erode mountains, unless you subside them, none of that ice contact deposition gets preserved, or very little of it. But the important thing is that if we know where the shoreline was, and we had an integrated depositional system, which we did in some of these cases, from the highlands to the shoreline, then you can place minimum elevations at the toe of the ice for where we think there may have been ice. And it's lower than it would have been during the LGM. And then I'll make one. Sorry.
But no, but you're okay. So let's assume there was ice in these mountains. That also, I think, feeds into John's concern, because then you're going to have, you know, local or at least regional environments that are affected by this ice. And, you know, part of the problem with all this, to me, it's kind of like the difference between allocyclic and autocyclic drivers of sedimentation. The allocyclic things are easy to understand. They're a big deal. I've got ice ages and I get cyclothems, blah, blah, blah. But now we're trying to get down to maybe a more detailed understanding based on tectonics. The ice would have created microclimate or local climate in wherever it was. I mean, I would argue that none of these Carboniferous Permian amphibians could cut it in ice. So if you were a little amphibian, you weren't living where there was ice on an ancestral rocky mountain and all that. So, and I don't know, you know, we've kind of ignored.
And where you're finding them, you're not in the mountains. So yeah, they weren't living where the ice was, for sure.
Right, but you know, when you look at I'll show this in my talk on the last day. When you look at the distribution of Carboniferous vertebrates, there's almost nothing from Gondwana. And of course, that's kind of easy to understand because it was probably just too cold in Gondwana a lot of the time for any of these early amphibians and reptiles. Nobody thinks they're warm-blooded where they would have lived.
Yeah. I mean, you could think of a place like, I don't know, Nevada, right? Nevada is full of basically island ecosystems that are in the mountains, and then they're surrounded by places where there is nothing in common with what lives in the mountains, right?
Right. Well, and the biologists have a name for that. They call them sky islands. And the idea is you're some little mouse who can live in cool weather in a mountain range, and you can't get to the next mountain range. You're effectively isolated. And they've studied, you know, since the end of the last ice age in Western North America, there's been a lot of research on how the loss of the ice and the changing of climate. So the basin and range, the basin floors are too warm for a lot of animals, and you get these sky islands. So you have to wonder how much of this, maybe the whole Cantabrian flora is just a sky island of sorts in northwestern Spain. How's that for an objectionable supposition, John?
And I'll make one other comment about the volcanism, which is that the volcanism that was taking place and that we have a record of in Germany and France and so forth was not actually associated with the collision, with the convergent stuff. It was associated with the collapse of the Variscan Mountains. And so it was actually essentially continental rifting, but intracontinental rifting, and it was extremely explosive. We have evidence for calderas and ignimbrites and so forth. And when you plot all those together, there's a hot spot. I mean that not in the traditional geologic sense of a hot spot. I mean that there's a concentration of explosive volcanism in Western Europe at this time. I mean, sorry, when I say at this time, I don't mean Kasimovian, I mean during the late Paleozoic, broadly speaking.
Yeah, I fully agree with that. That's exactly the point I was hoping to get to. That, it's an element of our interpretation of what's happening in the late Paleozoic, which we must not ignore, in my view.
Mm-hmm. Okay, John Isbell, do you have a comment? Were you raising your hand to say something?
Yeah, I was just going back in terms of uplift, and a lot of that has to do with where we are in terms of paleolatitude. Certainly, to get ice and changing conditions close to the equator, you have to have pretty high elevations. But if you're in the mid latitudes or high latitudes, you don't need to have a lot of elevation to create orographic effects and rain shadows and so forth. 800 meters, a couple of 100 meters could make a difference. And when you start looking at climate modelers and where they have glaciers forming, they're always forming on uplifted areas, but get rid of those uplifted areas in some fashion and you can't nucleate a glacier, or try to nucleate a glacier in the rain shadow. It just doesn't happen. But you don't need really high elevations. 800 meters might be enough in that case, if you're close to one of the polar regions. But as you go farther north or south towards the equator, obviously that rises.
Bill DeMichael has comment in here. Bill, do you want to join this?
I've kind of forgotten what it was. It was actually something different entirely, but I was just going to send Sophia a question to ask her if she wanted to comment on temperature, since I know she's a co-author on a manuscript that's done some work on temperature modeling. Sophia, do you think that's fair to talk about that yet? I don't know if that's actually sufficiently safely impressed to talk about, or if what do you think?
You mean Will's paper?
Yeah. Mm-hmm.
Well, I'll try to answer whatever question you might have to my best ability. It's in review.
I thought you did some of the modeling on that, didn't you?
Yeah, I did some of the modeling. Yeah.
And it comes up with very cold temperatures, very close to the equator during glacials. Is that right?
Yeah, particularly in the Genesis model, which, I mean, in CESM, which is, a different Earth system model, we get slightly warmer temperatures. But yeah, in Genesis in particular, we were getting very low temperatures.
So that might help what Lynn is arguing for as well, right? That you could have some really real, I mean, you're talking about really cold. And I realize it's a model that's got large ranges, but you're talking about what, -20 C and stuff like that? Were they that cold? Or more than that? Wasn't even like close to a -80 C or some sort of thing like that, but way down close to the equator.
Yeah, in those highland regions. Are you talking about the potential formation of equatorial ice and the plausibility of that?
Yeah.
Well, I also think, I forget the paper, but Nick Heavens, I think, published exactly on this, with CCSM3, trying to see if with what level of CO2 could you get down to in order to facilitate the temperatures that would allow for ice formation in the low latitudes. And I don't think he was, in that particular model, he went down to something like, Lynn might be able to speak to this, but 180 ppm, I believe. He went down quite low in CO2 and couldn't create those temperatures that would facilitate ice growth there. But it was one model, and I wonder what potential factors could have been contributing to that. I wish I could summarize that paper a bit better, but yeah, essentially that. I don't think, to my knowledge, that I've seen any models that have been able to create the temperatures that would sustain ice in the equatorial latitudes so far.
Okay, thanks.
Jorg has a comment. Jorg?
Sophia, let me ask you a question. This high input of organic carbon into the sea, could it be related to the release of methane hydrates because of a sea level fall or whatever? This could make methane could make this input hydrates, methane hydrates. What do you think?
Sophia, he's asking you, could this high increase in carbon have been the result of the release of methane hydrates?
Oh, I mean, I am not entirely sure just because that's not my expertise of I don't want to speak to it without having the other co-authors here able to speak to that. But all that I know is I think that's a potential possibility that it could have been, but I'm not sure.
Okay, think about.
Okay.
Could be an easy explanation.
Oh, Bill, you want to say something?
I wanted to ask Eric about the paleosols from the point of view of a field geologist. You know, you're in the field, you're clearly looking at a paleosol, and it almost causes me to despair to think that I have to sample it, take 25 samples from it, and send it to your lab to figure it out. It's getting like conodonts. Is there anything that somebody in the field who's out there measuring a section can say about a paleosol confidently simply from the gross morphology, or are we really talking about really broad limits on what we can say?
Yeah, you mean in terms of like climate interpretations? Yeah, unfortunately, I would say beyond like the end members and those end member soil morphologies being those that would contain gypsum, which is just, you know, obviously vanishingly soluble in water, or an oxisol, essentially just a bauxite, a pure aluminum hydroxide, and it might, in its diagenetic form, an oxisol might be purely kaolinite, since most of those minerals like gibbsite are metastable. But yeah, if you're dealing with a clay-rich soil, certainly a poorly developed soil profile, you know, you might argue that histosols and calcite-bearing soils are on the kind of wet to more semi-arid end members, respectively, but hard to be too precise with that. If a soil just has clay in it, you know, lots of, you know, where Spencer lives, there's lots of lovely clay-rich iridosols, you know, like it'd be really hard pressed to argue humid ever wet just on the occurrence of pedogenic phyllosilicates in a soil profile. So, but you know, if you don't want to do if you don't have the money or time to do like, you know, 25 samples per profile, just characterizing the parent material and like a B horizon, like a really obviously developed B horizon, would be a decent way forward to quantify that.
What do we do with the older literature? Because there's a number of publications, I think, papers on soils in Kansas from the Missourian, which are, you know, roughly at the level of Garnett, Kansas, which is, you know, classic site, or some of the Conemaugh soils in the Appalachians that are from the older papers, not from the newer ones. Can we use those effectively, or should we trust what their interpretations are?
Well, I'm not too familiar with those particular soils. I couldn't speak to any detail on that, but yeah, I mean, I guess the unfortunate answer I would say is that a conservative standpoint would be it depends on what they're finding. You know, were it me, if they have geochemical data, then yes, you can use that. I mean, for example, the proxy that I developed, I used data from 1935 from the North American Atlas of Soils. You know, like we were collecting that kind of geochemical data in the early 20th century. So, you know, my hope would be that that kind of data would exist for those older papers as well.
Spencer, can I ask a question?
Yeah, go ahead, Merlin.
It's for Phil Heckel. We've found radiolarians associated with several of the black shales in north central Texas. And then my wife and I described a bunch of radiolarians from the Des Moines of Iowa. One question we'd like to ask Phil is, where do you think these things came from and why are they in shallow water, so-called shallower water anyway? And what's the youngest and oldest radiolarians that he's had reported in the farthest east he's seen them? Because here in north central Texas, we got them at least 4 cycles now. They're very scarce and very weird as far as preservation is concerned. Now in Kansas area, they occur in the Des Moines and Missourian. It seems like in north central Texas, they're in the Des Moines and Missourian. And we're just curious to know, my wife and I, she happens to be in Russia at the present time, but we're going to talk about these things at InterRad in the fall, hopefully. And we'd kind of like to know what's the youngest that Phil has ever seen any radiolarians in the Pennsylvanian anywhere, and what's the oldest? That's my question.
You there, Phil? I don't know if Phil's there. He
disappeared.
He may have stepped out for a minute. Let's get back to that with him. Hopefully, Xiangdong Wang has some questions or comments on both Phil and Sophia's talk. So if Xiangdong can join us and make comments, we'll come back, Merlin, if Phil returns.
Okay, thank you.
Yeah, it's a wonderful talks today. And for Sophia's talk, I would like to give some background. When we work on the Naqing and Nalao sections, just below the gazetting boundary, we found a black shale. So in Naqing section, just 20 to 30 centimeters black shale, and in Nalao section a little bit thick, about 50 centimeters thick black shale. And we have another slope facies section we call the Sanlong section. Also, we have this black shale. So I think this is when we found this black shale, we realized maybe something happened around the boundary. So we tried to do uranium isotope and focus on this carbon isotope. So we found we think this is a kind of warming event. So this is we try to do more detail. So yogurt rice is a really good idea, and we may can do some more geochemistry and to look for what's the real reason. And in South China, there's no any volcanoes happen around this boundary, but in Carboniferous and the Permian boundary in North China, there are some volcanic events. This is one I would like to give some information. And for Phil's talk, actually, Kasimi we know as senior also, we published one paper in GSL special publication 376. We do the shallow water facies, shallow water section in Zhongji section. Probably Phil Heck visited that section, and we recognized around 30 sequence boundary, or we call the the depositional sequence. This we correlate this 30 from late Muscovine to acetylene. We recognize the 30 depositional sequence. We correlate them to the cycloseme, major cyclosemes. We tried to correlate them. So I think this is controlled by glacial static sea level change, I think. So we try to do correlation, shallow water, this kind of sequence to the deep water. We is notching section. We can see differ notching section into the many cycles. So we try to do this later using the sedimentology and other method. Yes, this is just a common.
Okay. I wonder,
And
Phil returned? Has Phil Heckel returned?
I think all Chinese and Japanese already went to bed. This is too late now. We already midnight.
No, I'm back. I had to go out and get the empty garbage cans in. Empty garbage cans in because a windstorm came up and there's thunderstorms due today.
Was there dust too outside? Was there dust coming down?
I didn't notice.
So Phil, did you hear Xiangdong's comment? He talked about a section that he and Katsumi Ueno worked on in China where they found, what did you say, 30 sequences or cycles? Maybe you can summarize, Xiangdong?
Oh, yes. Yes, please, please mention it.
Xiangdong, can you tell Phil again?
Yes, from Moscow to acetylene, we recognized about 30 sequence boundaries, and we tried to correlate those boundary to those this sequence to the cyclotheme, major cyclothemes. So,
okay. But the major cyclothemes are up on the shelf, aren't they? Separated by paleosols. On one of the field trips there years ago, I saw, the Chinese leaders showed several different cyclothemes, but they were mainly shallow water limestone separated by paleosols. That would have been South China on the platforms.
Okay, yeah. But we think this is also controlled by the glacial eustatic sea level change.
Yes, yes. I think
this is not local. This is not local, I think. So we found several sections in South China.
Was this published in one of the
GSL special publication? Yes.
GSA.
GSL.
Oh.
Special publication 376.
If you could email me that or email.
Okay, I will send the paper to you.
Yes, please do, because I do remember at that convention, the Nanjing Congress, that somebody did have a paper where they were correlating. Is that correct?
Yeah. Yes.
Yes. Okay. I may have seen that, but I'm at home right now, and I have piles of paper in my office, which I can use also, but I have all my setup here at home.
So also, Xiangdong, can you upload that paper to the Dropbox folder for the literature for the meeting?
Okay.
Remember, Bill sent everybody, again, I'd encourage you all, any and all of your publications relevant to the workshop, you may just upload them into Dropbox for all to download and read.
Okay, as long as I can get into the Dropbox.
Okay.
I'm still rudimentary.
Well, now wait, you're not off the hook, Phil. Merlin Nestel had a question. He said he's got radiolarians in the middle to late Pennsylvanian of Texas, and he wanted to know, to your knowledge, what are the oldest records and the youngest records of radiolarians that you're familiar with, I think, in the Pennsylvanian?
I don't know, but I know John Pope would know.
Okay.
John Pope has published with Merlin.
Okay, so that would solve that.
And John Pope was the guy dissolving the big calcite nodules in these black shales and finding fantastic stuff, which then Merlin and Galena worked up with him.
Okay. So Matt Stimson has a question. I think this is going to bring us back to the discussion we were already having about alpine glaciers and elevation. So Matt, if you want to turn on your video and audio, please.
Yep. Hello, everyone. Great talks today. So I work in Atlantic Canada in the Maritimes Basin and do a lot of work at a place called Joggins, UNESCO World Heritage Site. And we're talking about microconchids being marine and some debate whether they are or not. We have microconchids encrusting on virtually every limestone, or within every limestone in the Joggin section. We've got about 14 parasequences in that section, where we go from well-drained to poorly drained to open water lithofacious assemblages. And in the open water, poorly drained boundaries, we typically have a coal overlain by a thick organic rich limestone full of aquatic biota, absolutely no marine biota, no brachiopods, no crinoids, or any microfossils. Yet the microconchids are encrusting on bivalves, plants, in virtually every one of them. Now, Joggins is thought to be typically, it is earlier than Kasimovian. It's, we're back in the early Pennsylvanian, but, Joggins is typically thought to be entirely fresh water. Some have argued possibly brackish, and we've got a lot of horseshoe crab tracks at those same lithofacies boundaries between poorly drained and open water. So horseshoe crabs are saltwater animals that have a very high salinity tolerance. So I'm wondering if perhaps some of these low mountains we're talking about, possible alpine glaciers, could be providing enough freshwater plumes into these localized basins to make them regionally brackish enough for lycopsids, tetrapods, and what we would normally see in freshwater continental environments, yet during high sea tracks to have enough salinity coming in and be at least distally interconnected with marine environments, that some of these critters may have a high salinity tolerance coming into areas we wouldn't expect them to be. Comment, throwing it out there.
Let me make one comment about the microconchids. My understanding is that they're not a paleosalinity indicator.
Yeah.
In that they are not, they're not living. The best you can do if you have microconchids is conclude, again, it depends on your perspective, but conclude that there was at least intermittent connection of this freshwater body with the sea. And I might point out that
wait, Ron, why would you conclude that? If they're not a salinity indicator, why would you conclude there was an intermittent connection to the sea?
Well, if they are lophophorates, they need normal marine salinity, but they can be transported during spring tides or storms, things like that, into low-lying coastal lakes. That's the thought that is behind this intermittent connection. But they're not a paleosalinity indicator. They're just they originate in the sea, but they're able to be transported into these freshwater settings if you're close enough to the sea and have some sort of intermittent connection. And let me make one other point before I forget, and that is that there have been a number of instances here in the Glenshaw Formation where we can trace the marine units laterally into these microconchid limestones. And that was actually done by a fellow by the name of Morris decades ago, but I've seen it in the work that I've done and with a number of marine units. So they are the up dip or landward equivalent of these marine units.
Jorg, did you have a comment on that?
This may be true that you have them in brackish environments, why not? But in Central Europe, we are 2,000 kilometers far from the next sea coast, and microconchids are common in lacustrine limestones. They are common in black shales, Neargeny black shale, well known to the vertebrate paleontologists. They are millipedes, completely encrusted by Spirorbis or whatever we call them. And the same for plants remains. So very far from any coast, any sea coast. This is
no physical connection.
They are true freshwater.
Bill, did you have a comment?
Yeah, just a couple of things. One, Vic Schema, who's at the Pennsylvania Survey, told me that one time he had, I forget what isotopes they did on some microconchids, and they were not marine. And he tried to discuss that with some of the folks who were claiming that they were marine, and he couldn't even get them to talk to him about it. They just didn't want to hear it because they were marine. So there's a problem there, and I think that was never published. He also, not him, Blaine Cecil has sort of beaten into me by being in the field a lot with him, not to call them freshwater limestones, but to call them non-marine limestones, because you could have limestones forming in environments where they're not in connection with the ocean, and they're full of salinity because of the drainage of whatever's in the local, especially if they're closed basins. There's no what have you. You can have a buildup of salts. And I don't know what that would mean for a microconchid. If it were perceived, marine salinity may mean certain kind of micronutrients and things that you don't get in an interior basin. I don't know their biology, but I think we need to be cautious with the word freshwater.
We have some non-marine lacustrine settings in earlier Carboniferous rocks in the Maritimes Basin. And what we typically see is some really weird evaporites, some calcium sodium sulfates like globerite and thenardite starting to be deposited. I mean, that's into fully lacustrine settings, but we're not really sure what the source of the salt is, whether it's either some older salt deposit that's eroding in, or if you're getting some sort of a volcanogenic sodium or calcium coming in through groundwater. We have no idea, but they tend to be very bad for anything alive in those lakes. And when we start to see those deposits, they become pretty much eutrophic.
Maybe the take-home message here is these things were euryhaline, and they're found in I mean, I'm going back, and you correct me if I'm wrong. A few years ago, Beth Kordesch and others published a paper arguing that they were marine. Am I correct in that? And then
no, not that they were marine, but they demonstrated a marine connection.
Yeah, exactly.
Body of water which they were found.
Right, and then Zayton et al. Critiqued that. There was a pro and con. There was a rebuttal and all. And you know, maybe they change in time periods, but again, I have a Triassic reptile skull that was 1,000 miles or 1,000 kilometers from the Pangaean shoreline, covered with microconchids. So, you know, it could be that you're right, Ron, that your microconchids are coming in through the marine connection, and you're making, I mean, the reason we're talking about this is correlating, right? Appalachian Basin limestones to marine cyclothems. That's why, I mean, it's funny, we had a whole day of climate and dust, and it all comes down to a bunch of paleontologists arguing about what some squiggly little things, like what kind of water they lived in. But that's paleontology, right? But yeah, it could be that you're right, Ron, that yours are coming in through a marine connection. But these European basins are these closed lacustrine basins. And you're right, they may not be strictly, you know, agua dulce, fresh water, right? But nonetheless, how did those microconchids get into those Variscan basins? There's no marine connection. And, you know, nowadays, here in New Mexico, we have foraminifers living in playa lakes, okay? And we know that they get there on the feed of shorebirds, on seagulls. They go dormant or whatever, and the birds bring them in. There are no birds in the Carboniferous to bring microconchids into Variscan lakes. So they and you know, we can't blame, I mean, you can blame it maybe on the feet of amphibians. I mean, I've already blamed something on amphibians. But no, this is an interesting problem.
Quick question for York, if I may.
Sure.
York, do you see any trace fossil evidence of, say, Kouphichnium trackways or assignable to things like horseshoe crabs? We have no, you know, at Joggins and in the Maritimes Basin, we have really no marine evidence in the Pennsylvanian, but I've long suspected that we have, you know, as Ron is pointing out in Appalachian Basin, that we have, you know, a marine connection, not just because of the microconchids, but also because of the trace fossils. We have these horseshoe crabs, which are, you know, if you go back into the treatise on invertebrate paleontology, it basically says horseshoe crabs are saltwater animals, except in the Carboniferous, in the Pennsylvanian, at Joggins, but because there's no evidence of marine critters, but we know that they have a very wide salinity tolerance. So do you have any trace fossil evidence that there might be a distal connection, even if you're very far removed from shorelines, that they might be traveling?
no indications. But we have also this Xiphosuran, this very small horseshoe crabs in the lake deposits of Central Europe. They are common. They are freshwater adapted. Spencer, you know, this nice Eurypterids from Kasle is not published yet. We have them in a lake now in the early Permian of Europe. Singular occurrence. Anyway, Lynn, in '94, I published a summary in English. You could read it before 2 papers in German. And there we support, or we come to the conclusion that marine higher algae occur in a basin in Central Europe, and they may be transported, cysts may be transported by wind into this basin. This is completely that is a typical Tedian higher algal flora, calcareous algae, and no idea how they could come into this basin if not by transported, if not the cysts are transported by winds, by storms, hurricanes.
John, you have a comment? John Isbell?
Yeah, Matt, I've been in the field with Steve Hasiotis in the Buckley Formation, that's Permian in age in Antarctica. And it's fluvial, and it's thought to have been fluvial for at least 500-600 kilometers down the basin. And he was walking around saying, that's a horseshoe trace fossil, that's a horseshoe crab trace fossil, that's a horseshoe crab trace fossil. He might be someone that you could talk to. I mean, it's Permian, not Pennsylvanian, but he seemed to think they were quite common in non-marine settings, at least in the Permian.
So something that we, my colleagues, I know Spencer was on the paper, as well as Olivia King, who's here with me beside me. Olivia published a paper from the Union Chapel Mines, and we know that they certainly have marine incursions, but we've also shown now, or at least we think, that some species of Kouphichnium, which are classically thought to be entirely made by horseshoe crabs, could also be made by other chelicerates like Eurypterids. So if some of these Eurypterids are making their way up fluvial systems to mate and molt, as other authors have believed to be the case, then I don't see why you couldn't get a Kouphichnium horseshoe crab-like trace in fluvial systems and even up into lacustrine systems. I'm seeing them in the Mississippian as well, and in the Maritimes Basin, in freshwater lakes, which are thought to be only periodically connected, where we have Eurypterid cuticle, but we are far from a shoreline in the Mississippian. So,
well, let me, you know, we're technically out of time now, and I see this, you know, to me, this is a classic argument that we have in many places in the rock record. What is salinity in the depositional system? In particular, what does the fossil biota tell us? Is it, I mean, and you know, this plays into big arguments. Like you talk about the origin of tetrapods, the origin of amphibians. There's been a big argument for over a century whether tetrapods originated in fresh or marine or nearshore marine waters, and it goes on. So, and of course, being a paleontologist, I know that we paleontologists have a capacity to talk about things forever. And so this discussion is good. It can go on, but I think we should end it unless somebody has a really burning comment. Oh, and Shandong Wang has just sent me a message. That paper he was talking about, Phil and all of you, with Ueno, it's now in the Dropbox folder for the meeting. So if you want to see that paper, please go there. And so again, let's bring it to a close now. I look forward to seeing all. We had a great day. What a wonderful set of talks, and I look forward to seeing you guys tomorrow. And I want to encourage you again. upload your published work into the Dropbox folder. Just don't assume, I mean, that everybody has your papers already. There's already a fairly substantial list. That paper you wrote in English, Jorg, you should put it up in the Dropbox folder. Bill has a comment here.
Yeah, the Dropbox folder, which if many of you are not familiar with Dropbox, if you take something out, physically take it out of the Dropbox folder and download it to your computer, it will disappear for everybody. So if you, it's because it's shared among all of us. So if you wish to take something from the Dropbox folder, please copy it and paste it into your own folder. Don't drag it out on your computer, or it will disappear for everyone. So you can copy things and paste them, but you can't take things out, or that we'll all see it happen.
Yeah, that's true. And of course, it's best, like it works best if you have your own Dropbox folder, which you can get for free online. And then what it allows you to do is simply copy it into your Dropbox. And then that way everybody else has access to it. But that folder will be around for the rest of the meeting. It'll be around after the meeting. We'll figure out what its lifespan will be, okay? And hopefully everybody can download. There's already a substantial amount of PDFs up there in the folder. Okay, so let me end today by thanking the speakers. What a great bunch of talks. Let me remind everybody, one thing I think some of the speakers today didn't remember is when you give your talk, turn on the chat, because it's in the chat that you're going to be given a 5-minute warning and a 2-minute warning for the ending of your talk. So for those of you speaking tomorrow, please do that. And then that way, I mean, we're fine. Some people got a couple of extra minutes. Phil Heckel got like 4 extra minutes out of me. But then again, if anybody
notice the chat, I didn't notice the chat box until after everybody else had talked. I mean, until later, I said, "Oh, I've got 2 chat messages."
Yeah. So if anybody, what I was going to say, if anybody deserved 4 extra minutes, it's Phil. And so thank you guys. We'll see you tomorrow. The organizers will stay here, right? We'll talk the meeting technical. Adios.
Bye, everybody. Great
Da zawtra, zajchen, everything.
Thanks, everyone.